Hello and welcome to the. So today, in continuation of the last class, we will discuss about the volatility models, where we will be discussing the multivariate gauge models, but it will be extension of this multivariate gauge models. So in the last class, what we have discussed that we have moved from univariate gauge models to the multivariate gauge models due to the limitation of univariate gauge models, where we assume that the volatility of particular asset is not being affected by the volatility of other assets. Similarly, it does not have any effect on the volatility of other assets. So that means there is no correlation, there is no co-movement of the volatilities among different assets, which is a very restrictive approach to the real world. And we have seen that there is the volatilities of the two different assets, they move together across the assets and also across the markets. And this was the one reason why we have switched to the multivariate gauge model, where we assume that the volatility of one asset could have impact on the other and other volatility could have impact on the first one. So volatility of assets may move together, and that is also true across the market. What in general term it is known as the volatility spillover. For example, the volatility in the US financial market may have impact on the other financial markets across the world. Similarly, the volatility of the equity market may have impact on the commodity market, or within the equity market, volatility of one particular stock may have impact on the others. So there is the co-movement among the volatility of across the assets. So that was the one reason that we switched from univariate gauge models to the multivariate gauge model. Another important factor was that there are the certain situations in the financial market and the financial econometrics and economic financial models, where we are not only concerned about the variance, we are also concerned about the covariances of the assets. For example, while calculating hedge ratio, we are concerned about the covariances of the assets, not only the variances. Similarly, in case of we wanted to evaluate the value and risk of the portfolio, there also we are concerned about the covariances. And the capital asset pricing model betas, where we have seen that the covariance does matter for the betas in the capital asset pricing model. So there are the certain situations where we are not only concerned about the variances of the financial instruments or the financial market, but we are also concerned about the covariances. And for that reason, we switch to the multivariate gauge models, or because of these reasons, facts, multivariate gauge models were proposed. And a general framework multivariate gauge model could be represented by this particular equation, where this yt is equal to mu t plus epsilon t, where this epsilon t is conditional upon the information of t minus 1, which follows the normal distribution with mean 0 and variance covariance matrix ht. So here this yt is the basically vector of n assets or n times series variables, and mu t here is the constant conditional mean vector, and epsilon t is the vector of residuals of all the series. And this ht is the conditional variance covariance matrix of epsilon t, and ft minus 1, it shows the information set available at time t minus 1. So then in that case, in the multivariate gauge models, we are concerned about this ht, that conditional variance and covariance matrix of epsilon t, which could be modeled in this framework, where the first term represents the arch effect and the second term represents the MGARCH effect. So in this equation, this C is the positive semi-definite matrix, that is the constant component, and this AI is the matrices capturing the arch effect, that is the impact of the partial residuals, and this beta Bj is the basically matrix capturing the GARCH effect, that is the impact of the past covariance. So this we have discussed in the previous class in form of multivariate GARCH models. However, there is another approach, what we call the conditional correlation models instead of So that is basically, this model is nothing but the extension of the multivariate GARCH models, where basically we take the different approach, and rather than modeling the dynamics of the variance comatrix, variance and covariances, we can directly model the dynamics of the correlations. And in fact, this correlation between the set of pair of variables or series at each different point of time can be constructed by dividing the conditional covariances. This we divide the conditional covariances by the product of conditional standard deviation obtained either from the VCH or the BKK model. So basically we know from the formula of the correlation, that is nothing but the covariance between x and y, then we divide it by the standard deviation of x and standard deviation of y, and that is nothing but the correlation between x and y. So the same the definitional approach here we use. So this conditional covariance of the different assets, that divided by the product of conditional standard deviations here. So now in case of multivariate GARCH models, we focus on the variance or covariance matrix. However, in case of conditional correlation models, we are not focusing only on the covariances, rather than directly we try to capture the dynamics of correlations, that is the conditional correlations. Now the question comes, why we should do that, or why we prefer the correlation models. So one of the reason is the curse of the dimensionality. So what is the curse of dimensionality is that in case of multivariate GARCH models, if we increase the number of the series or the number of financial assets on instrument, so the number of variables, if it increases what we call the high dimensions, in that case we have to estimate a large number of parameters. So that's what we know as the curse of dimensionality. Because if the large number of parameters increases, then the computational challenges increases, and in fact there will be the quadratic growth into the number of parameters as the number of variables, what we here we call it as the dimensions increases. So one of the difficulty we have in multivariate GARCH models is the curse of dimensionality. The second issue we face in the multivariate GARCH models, because we are focusing on capturing the dynamics of the covariances among the different series, then in case of covariance we have the interpretability issues, that it is not easy to interpret those covariance parameters. However, if we use the correlation, it is easier to have, and it have more intuitive meanings compared to the covariance. Further, in case of correlation, we get the magnitude as well as the direction of the correlation, which makes much more intuitive sense compared to the covariances. However, there are the certain issues we have in both in the correlation matrix, conditional correlation models or approach, and also we have certain the difficulty in approaches of the covariances. Out of those two here we have mentioned, which is the basically the major reason why the conditional correlation models were developed and proposed. In general, we can summarize those that the multivariate, and another important point to be noted here, that both these models has its own advantages and disadvantages. In case of multivariate GARCH models, that is more suitable when we have less dimensions, less numbers, and we wanted to capture the more detailed relationship, then it is better to adopt the multivariate GARCH approach. And where the concern is about the covariance dynamics rather than the correlation. However, in case of the conditional correlation models, it is better suited when we are concerned about the high dimensional system where large number of variables is concerned. Because in that case, is the this part conditional correlation models becomes computationally efficient and it is focused on interpretable correlations. So both these models have its own advantages and disadvantages. Depending on the context situations, we would prefer some multivariate GARCH models, and sometimes we would prefer the conditional correlation models. Basically, in conditional correlation models, we decompose the variance covariance matrix from the multivariate GARCH model into the two parts. One, the conditional variances, basically which is the diagonal elements of the covariance matrix, and the second constituent of the decomposed part is the conditional correlation, which is basically of diagonal elements. And how we treat the conditional correlations, based on that we could have three types of conditional correlation models. One is known as the constant conditional correlations, another is the dynamic conditional correlations, and third is asymmetric dynamic conditional correlations. And all these three models has certain advantages and disadvantages and capture some specific aspects. So let us discuss one by one here. So the first model, that is the constant conditional correlation model, was proposed by Boller-Salev in 1990, assuming that the correlations are constant across over the time. So it is not changing, and the variances basically follow a univariate GARCH process. So based on these two assumptions, he proposed the constant conditional correlation model, an extension of the multivariate GARCH model, where basically we do the reformulation of the variance covariance matrix by decomposing it into the two parts. One, what we call the conditional variances, second, what we call conditional correlations. So here the time script T represents that we are assuming that conditional covariances are dynamic time varying. However, absence of T subscript in R, it reflects that we are assuming the correlations are constant over time. So this dt, basically it is nothing but the diagonal matrix where it represents the conditional covariance of, let us say we have the two assets, the first asset and the second asset, where this conditional covariances are basically where this dt is the diagonal of this conditional standard deviations here, and this basically is modeled in univariate GARCH process. Here omega I, for example, if we have the two assets, then for the first asset what we have h1t is equal to omega 1 plus alpha 1 epsilon 1 t minus 1 square plus beta 1 h1t minus 1. So here this is for the asset 1. So in this case, this is nothing but the variance at time t, which depends on the constant omega plus the arch effect, that is the square of the past residuals, plus it also depends on the lag variance. So this is nothing but what we have, the formulation of GARCH 1, 1. So this is the gauge. So here we are assuming what? That this variance structure, it follows a univariate gauge process. Then this R, which is the conditional correlations, it follows this particular structure in case of the two variable. That is, here we are assuming this rho is the nothing but the conditional correlations, and these are the constant. To have a better idea, let us take the two variable situation where this HT, the conditional variance and covariance matrix, it has been decomposed into the two part. One, these are the diagonal conditional standard deviations, here this part, and this is nothing but the conditional correlation matrix we have. Now if we multiply that, then the conditional covariance variance and covariance matrix becomes this, where these diagonal elements are the conditional covariances, whereas these are the basically conditional correlation matrix. So these are the basically what we know, the diagonal elements, and these are the off diagonal elements. So off diagonal elements of the variance and covariance matrix HT is here the conditional correlation matrix. Correlations, whereas the diagonal elements of the variance and covariance matrix, that is HT, is nothing but it is represents DT here. However, the assumption of constant correlations is quite restrictive, and how we deal with that, so we'll discuss just after this. So what is the estimation process we have? In case of conditional correlation, constant conditional correlation models, we follow a two-step estimation process. First, in step 1, we estimate the univariate GARCH models for each series independently and obtain the estimated variance here. Then in the second step, we use this estimated variance from the univariate GARCH models for individual series, use that standardized residuals from step 1 to estimate the constant correlation matrix here. Then we use this maximum likelihood estimation function, and we estimate the parameters here, where this HTA is now in the form of this particular structure, that is the decomposed of two parts, conditional variances and the conditional correlations. In case of constant conditional correlations, what we have assumed that correlation is not changing, which is a quite restrictive approach. In the reality, it is in the real financial market or the real world, what it has been observed that correlations between the two assets or even across the markets do changes. For example, what we have seen that whenever there is the crisis in the economy, there will be more correlation will be increased. However, when there is the economy in the boom, the correlation may decrease. So the correlation doesn't remain same across the assets or across the markets. Therefore, the dynamic conditional correlation model was proposed. So where the assumption is that the correlations vary over time, it is no constant, and the same the variances follow a univariate GARCH process. So what the mathematical formulation there has been changed is that here the RT now have the time subscript, so that reflects that the conditional correlations are also time varying, or what we call dynamic. So in that case, this RT then, this conditional correlation matrix is constructed using this structure, where this QT is nothing but alpha 1 minus alpha minus beta into Q bar plus alpha ZT minus and ZT minus 1 transpose of that and beta QT minus. Here this alpha beta are the parameters, where this ZT is nothing but the epsilon 1T divided by the conditional covariance. And this Qt star is nothing but the diagonal of Q1 and Q2, where this Q11 and Q22 is nothing part of this matrix Qt. And this Qt depends on this particular structure. So that's what we call the dynamic conditional correlation. So here it is depends on the time period, and it depends on this the value of error terms and the changing standard conditional covariances. So if these two are the dynamic, then this Qt is also dynamic, and if the Qt is dynamic, then this conditional correlations matrix also becomes dynamic. For example, again to understand better, let's take the example of the two variable case. Then what we have for the Qt, what we have Q11, Q12, Q12T and Q2T. Here this RT is nothing 1 upon rho T upon rho T. So that is the conditional correlation matrix. Here we are assuming that it is time varying, and this rho T, that is the correlation at time T, is calculated using this particular structure. So the conditional covariance between two assets, that divided by the standard deviation of Q11 and Q22 at time T. So it is changing here. How to estimate this dynamic conditional correlation model? So again, it is same like the conditional correlation model. We can estimate this model using the two-step procedure. That is, first at the first step, estimate the univariate GARCH models for the each variable to obtain the dt. That is the conditional covariance. Then at the step 2, we use the standardized residuals from step 1 to estimate the Qt, and once we estimate the Qt, then we are able to estimate the RT. So again, the two-step procedure we have. However, this model also has the certain limitations. What limitation it has? That it has assumed that the correlation is changing. However, what it has been observed that the correlation is not only changing, there will be more fluctuation in the certain period, and in the certain period there will be less fluctuations or the less variability into the correlation structure. So to capture that, what we have the known as asymmetric dynamic conditional correlation models. So basically where we assume that the correlation will be changing, however the variability will be different into the crisis and when the economy is in boom or when the economy is stable. So what it has been observed that during the downturns or the crisis, usually the correlations increases. That means there is the asymmetry into the dynamic conditional correlation, and to capture that, the asymmetric DCC model has been proposed. So for that, what we have, basically while calculating the Qt, that is the diagonal Qt, we have another term, an extension of the terms which we have into the dynamic conditional correlation model. So here we have all these we have in the previous model also, which then here we have in addition to these, we have this gamma eta t minus 1 and eta t transpose t minus 1 here, where this eta t is basically is zt and Hadamard product of I into zt when zt is less than 1. So when zt is the less than 1, that is when the market is down, then what we have, it becomes 1. Otherwise, what we are assuming, otherwise it is 0. So when it is 0, then we have the same as we have in the dynamic conditional correlation. However, when this zt is less than 0, in addition to that, we have this particular term which goes into the Qt, and then only it goes to the RT, that is the conditional correlation matrix. So this captures the effects of the negative shock because this zt depends on the epsilon t, that is nothing error term into the mean equation. So this gamma parameter here, this controls the effect of negative shocks on the correlation matrix. So if it is not negative, then this particular term becomes 0 and lambda does not capture that. However, when there is the negative change, that effect is being captured by the gamma. So which basically reflects that the correlation increases during the market downturns or the crisis. If that is the case, we have additional correlation is this. If there is no downturn or there is no crisis, market is normal or it is boom, then this particular term is not added into the correlation. So this fact that the correlation increases during the market downturns is being captured by this particular term, and that's what we call the asymmetric dynamic conditional correlation model. So in that case, we have already discussed, we capture through this here. So what are the advantages we have of this model? Accounts for the asymmetric correlation during the market downturns, and it is suitable for the stress testing. So what is stress testing? We have discussed. So stress testing, basically what we mean or what it refers that if there is the adverse situation or if the plausible adverse situation is there, so in that case how the market reacts or how the performance of the different financial assets changes. So that's what we call stress testing. How the market performs in the plausible adverse situation or how the financial asset performs. If so, that is basically what we call the stress testing. However, it has some limitations. What limitations it has? There is more computationally demanding structure we have. Then how we estimate this model? So similar like the DCC, dynamic conditional correlation models, this ADCC, that is asymmetric dynamic conditional correlation, is estimated into the two steps. That is, in the first step, estimate the univariate GARCH models for each variable, and from there we get the HT hat, and then we use the squared residuals of this step to estimate the parameters of alpha, beta, gamma and QT using the standardized residuals which we get from the first step. So these are the primarily three extensions we have of the conditional correlation models. Now let us take the certain situations where we could use these conditional correlation models. So one of that is the financial risk management, or what we call stress testing, and the systematic risk analysis. For example, to test the market contagion, what is the market contagion is that when there is the downturn in one economy, that could have impact or that could be spilled over to the other markets. That's what we call the market contagion. And that means whenever economy is in stress, that the correlation across the markets will increase. So that we can assess using the either the dynamic conditional correlation models. So that could be used to study the increased correlation between US stock market and the emerging market, let us say in the 2008 global financial crashing, highlighting the contagion. If the conditional correlation increases, that means there is the contagion effect we have. If that does not changes, that means there is no contagion effect. Second application of this conditional correlation models we have in the portfolio optimization. In the portfolio optimization, basically we have the ratio of the certain assets to maximize the profit and to minimize the risk, which we have discussed in the previous lectures. So in that case, if you are assuming the correlation are the same, a constant over time of the two assets, that may be misleading and that may not be able to capture the changing market conditions, and that changing market conditions have impact on the portfolio optimization. So therefore, to capture that dynamic or changing conditional correlation assess the conditional correlations among the assets, so that you can optimize or your weights as given to the, or the weightage has given, you can, so that you can dynamically optimize the correlations between different assets. And similarly you can change the weight. So the diversified portfolio of each, and for example take and the energy stocks. So if we, for example, we can give the different weightage, dynamic weightage to the take and energy stocks in the portfolio. So that's what we call the dynamic asset allocation is possible using the application of dynamic conditional correlation models. Similarly, we can use these models in case of hedging strategies. For example, if you wanted to have the currency hedging for the multinational firms, if they wanted to evaluate what is the correlation between USD and the euro, and what is the USD and Japanese yen, so that can be captured by the DCC model, and that can be captured, that can give us that can help us to strategize the hedging formalities. Then stress testing the financial market, that could be done. Assess the asymmetric correlation during the crisis. For example, in the market downturns, let us say in the COVID-19, the spikes in equity commodity relationship. So if you wanted to see, in case of downturn, does the people have so for example, we wanted to examine, does the correlation between the equity and commodity market remain same, or is there any change during the crisis period, for example COVID-19. So for that we could use the dynamic conditional correlation the asymmetric dynamic conditional correlation models. Then it could be also used in the international trade and the finance. For example, exchange rates depends on the trade flows, and trade flows depends on the exchange rate. How? Let us say if our Indian rupee depreciates in terms of US dollar, that means the INR USD has reduced. If this is the case, then that means in terms of INR, the value of USD has increased. If this is the situation, then we have the two implications of that. One, our exports becomes cheaper for the US citizens. On the other hand, for us, we will get a more INR or more income. On the other hand, the imports from the US will become more costlier, and both these will have impact on the trade flows. So if the exchange rate depreciates, exports may increase and imports may reduce. So that means by tracking the correlations between the different currencies, we can predict or we can manipulate the trade flows, or we can analyze the trade flows. For example, the relationship between USD, Euro and British Pound exchange rates, we can track, is there any correlation or what is the dynamics is happening. The fourth implications where we could use these conditional correlation models is the commodity market analysis. For example, it can capture the correlations between the commodity prices, for example, oil and gold, oil and the food commodity and so on. So, and by looking the correlation structure, we can see what is happening in that particular market. So these are the few examples where we can use the correlation matrix here I have discussed. However, there is a lot of other aspects where we can use such models. So in the next class, what we are going to do is that we will take the two case studies where we'll be using these models, and we'll see how we estimate these models, how we will make the interpretations, and what are the implications we have. So see you in the next class. Thank you so much.